Hello, everyone, and welcome to our webinar, How Agentic AI Transforms the Role of Storage. Today's conversation is with Fatma Asmandian, Distinguished Engineer at Dell. Hello, Fatma, how are you?
Hi, Michael. I'm doing well. Hope everyone's doing well in it also.
Excellent. And we have John Cardente, Senior Distinguished Engineer at Dell. Hello, John, how are you?
Good. How are you, Michael?
Excellent. Yeah, thank you. We also have finally Hima Bintu Tumala, and she's a distinguished engineer at Dell. Hello, Hima Bintu. How are you? Okay. Now we've had a little bit of technical difficulty. We're going to cover the full webinar. Right now, there's a connection problem for Hima Bintu. Also, Fatima is traveling and might have to leave a little bit early. So we'll just get started pretty soon here. Before we get started, I want to just give a little bit of mention of the CST community. It's one of the groups within SNIA responsible for education and raising awareness on topics like agentic AI, use cases, benefits, and risks, as well as self-storage in a world of AI ML workloads. Please join the CST and other SNIA groups to help organize and promote these important activities. Next, I want to mention that SNIA is a group of about 200 industry-leading organizations comprising of 2,000 active contributing members and 50,000 participating IT end users and storage experts worldwide. SNIA develops global standards and delivers education on all technologies related to data. Now I'd like to take a quick look at the SNIA legal notice. This provides SNIA's copyright notice regarding use of the materials. There are no warranties expressed or implied, so if you want to reference this material, please do so at your own risk. You can download a copy of this presentation using the interface for this live webinar. The interface also allows you to submit questions during the talk and rate this presentation at the conclusion. We really appreciate your questions and feedback. If we are not able to cover all the questions during the session, we will answer your questions in a Q&A blog, which will be posted after this webinar. So let's get started. Fatma, please take it away.
Thank you so much, Michael. Welcome, everyone. Today, we're going to connect the dots between agentic AI and the evolving role of storage. Oh, excuse me. Apologies, I jumped ahead. We'll begin with an agentic AI overview. What distinguishes agents from traditional chatbots, assistants, and workflow-driven systems, and why the shift toward autonomous reasoning and action is such a major inflection point in AI capabilities. From there, we'll move into multi-agent systems and interoperability. As organizations deploy more agents, often from different vendors and running across on-prem and cloud environments, interoperability becomes essential. We'll talk about the emerging ecosystem of standards like MCP and A2A, and how they enable agents to discover tools, communicate, collaborate, and operate securely. Then we'll transition into the core topic, storage in the context of agentic AI. We'll look at how agentic architectures introduce new types of workloads, especially reasoning-heavy inference and KV cache behavior, and how storage plays a central role in enabling context building, real-time retrieval, semantic indexing, and data-driven tool usage. We'll conclude with a brief set of closing insights to tie everything together. With that, let's jump into the overview and set the foundation. We're witnessing a fundamental shift in how AI technologies are evolving, and agentic AI represents the next wave in this progression. Each wave builds on the last, but fundamentally changes what's possible. This journey began with predictive AI, where machine learning models were specifically trained to do narrow tasks like forecasting outcomes, classifying patterns, and recommending options. Generative AI used the power of large language models to perform tasks outside of their training dataset, like generating content and answering questions based on prompts from users. Now we're entering the agentic era, and this is transformative. Agentic AI doesn't just respond to prompts, it plans, executes multi step workflows, uses tools, makes decisions, and adapts autonomously. It's proactive rather than reactive. Instead of asking AI, write this email, you say, manage my inbox. And it does, making judgment calls along the way. And on the horizon, artificial general intelligence, systems that can understand, learn, and apply intelligence across any domain at human level or beyond. That's the long term vision, and we're likely still years away from reaching that capability, but AI is the bridge that gets us there.
Yeah, I apologize for
So,
the audio quality. John is ready to present. John, do you want to? I'm sorry that we're having this difficulty.
Yeah, absolutely.
John, yeah,
Thank you,
sorry.
Michael. Yeah, and apologies to the audience, and thanks for Fatima for trying to cover in a difficult situation. So
Yeah, she has an urgent matter going on now, so that so we apologize for this, but
yeah,
please go ahead. Thank you.
sure. Yeah, so let me pick it up on this slide. So what exactly makes an AI agent different from chatbots, assistants, and workflows we're already using? It comes down to one critical capability: autonomous reasoning and action. A chatbots answer questions directly from their training data. Ask, what's the capital of France? And you get Paris. It's conversational, but fundamentally static knowledge retrieval. AI assistants take it further. They can answer questions about your information using techniques like retrieval augmented generation or RAG. They'll search your data set, pull relevant context, and generate informed responses. Think of it as a chatbot with access to your filing cabinet. AI workflows add structure and orchestration. They execute predefined tasks by chaining together LLM prompts and predetermined actions. You define the workflow, extract this data, then format it, then send an email, and it follows your blueprint reliably. But AI agents, this is where autonomy enters the picture. An agent doesn't just follow your script, it accomplishes an objective by dynamically directing its own reasoning and actions based on what it observes in the environment. It perceives, decides, acts, learns, and adapts. Think of it this way: a workflow is like following a recipe, an agent is like a chef who understands the goal. Make dinner for four with what's in the fridge and figures out the steps themselves. That's the fundamental shift from execution to autonomy. Agents are essentially software built from four main components: a model, a system prompt, configuration parameters, tools, and memory. The model is an agent's brain, giving it the ability to observe, reason, and plan. The system prompt defines the agent's purpose and provides high level instructions on how to perform its tasks. Tools are an agent's interface to the outside world for getting information from data sources or initiating actions by calling services or sending requests to other agents. Long and short term memory gives an agent the ability to learn from past decisions and actions to improve its performance on future tasks. These components are integrated by orchestration logic or a harness typically implemented in software using a framework like LangGraph or ADK that simplifies the development of agents. The interface or API provides a way for the agent to receive requests to achieve an objective, whether that's from a user, another system, or another agent. Together, these components can create a system that doesn't just respond, it thinks, acts, remembers, and achieves goals autonomously. Although we tend to consider agents as singular identities, they're often built from a distributed collection of components. For example, agents may share the same reasoning model hosted on an inference server in an enterprise data center or cloud platform. In this slide, we have two agents, Agent A and Agent B. They're designed to achieve different objectives using different system prompts and tools. Agent A might be handling customer support escalations, while Agent B is processing expense reports. Different purposes, different logic. But here's the key efficiency play: a shared inference service. Both agents share the same reasoning and planning model, hosted by an external server with sufficient GPU capacity. Instead of deploying separate LLMs for each agent, We have one powerful inference service that handles reasoning requests from multiple agents. This dramatically reduces the infrastructure costs and improves resource utilization. Similarly, both agents use the same database service to store, search, and retrieve their vectorized content for building context. However, and this is important, Agent A has its own vector database and Agent B has its own. They share the infrastructure but maintain separate knowledge bases. This ensures each agent has access to the right context without cross contamination. The result? We get the logical separation we need. Each agent has its own purpose, prompt, tools, and memory, while achieving operational efficiency through shared services. Both human clients and other agents can interact with either agent through standard APIs. This pattern allows you to scale your agent ecosystem without literally scaling your infrastructure costs. You can deploy dozens of specialized agents, all leveraging the same underlying LLM and database infrastructure. Now let's dive into how reasoning models actually work. They use an observe, reason, and act loop to gather context and take actions needed to achieve an objective. This is the engine that powers agentic behavior. The process starts with an input prompt, the user's objective or question. From there, the agent enters an iterative cycle. First, the agent gathers context. What information do I have? What do I need? Then the model thinks through what needs to happen. In reasoning mode, it's generating internal thoughts, assessing options, and planning next steps. It produces a decision about what to do next as its output. If action is needed, it makes a tool call. That action becomes part of the observed context for the next iteration. The cycle repeats. Each time the agent observes the results of its previous actions, reasons about the new context, outputs its thinking, and acts again if needed. This continues until the agent determines it has achieved the objective and provides a final response. You can also limit the maximum number of iterations to avoid an endless loop. Let's look at a simple example. The user asks, "What's the weather like in Boston?" In the reasoning phase, the model thinks, "To answer this accurately, I need real-time weather data. I have access to a tool called Get Weather that can retrieve this information. I'll call this tool with the city set to Boston and use Celsius as the temperature unit." Then the agent acts on that reasoning, calls the tool, observes the result, and formulates a response. But here's a critical consideration. Reasoning can increase the number of context tokens by 10 to a factor of 100 versus non-reasoning large language models. Every iteration adds tokens, the original prompt, the reasoning steps, the tool outputs, the thinking process, and this significantly increases the computational infrastructure requirements for agents at enterprise scale. So there's a trade-off, more powerful autonomous behavior for higher compute costs. And this is why efficient orchestration and infrastructure sharing, like we saw on the previous slide, becomes so important. Next, let's talk about multi-agent systems and interoperability. So far, we've talked about agents as individual actors, but in real enterprise problems require teams of agents, not just one. As tasks become more complex, especially in business to business and enterprise workflows, you naturally need multiple specialized agents working together. Some agents execute predefined workflows, while others collaborate autonomously, deciding at runtime how to decompose objectives and coordinate execution. These agents likely won't come from the same vendor or run in the same environment. You'll have agents operating on your premises in your data centers or in the cloud, interacting with their internal systems, external services, and each other to automate real business processes end to end. To make this viable, agents operate with their own identities and act on behalf of others, either agents or users, so that policies can be applied consistently as work spans systems and organizational boundaries. Once you accept that this is a distributed systems problem, the need for interoperability becomes clear. As agentic systems evolve into distributed multi-agent environments, a common set of interoperability concerns quickly emerge. Interoperability for agentic systems comes down to four core concerns: discoverability, interaction, security and trust, and observability. For discoverability, agents need to dynamically find each other and understand capabilities at runtime. In large systems, you can't predefine every interaction. Agents must be able to identify who can perform a task, who has access to required data, and how to engage the right collaborators. Without this, collaboration quickly degrades back into static workflows. Second is interaction. Once agents discover each other, they need a common way to communicate and coordinate, regardless of framework vendor or deployment location. This includes task delegation, multi-turn exchanges, asynchronous requests, and coordination across long-running activities. Interoperable interaction is what allows heterogeneous agents to work together without custom integration at every boundary. Third is security and trust. Agents must have verifiable identities and provenance so systems can determine whether they're authorized to access data or act on behalf of users. This becomes increasingly important as agents operate across organizational and administrative domains. Finally, there's observability. As agents reason, invoke tools, and collaborate with other agents, we need end to end visibility into their behavior. This is essential for debugging, governance, compliance, and operational control in production environments. Systematically addressing these concerns using standardized protocols and services will enable agent ecosystems to scale beyond isolated use cases. To address the need for standardized interaction in agentic systems, two protocols have emerged, MCP and A to A. The Model Context Protocol, or MCP, is an open standard designed to securely connect AI systems with data sources and servers, such as content repositories, databases, and APIs. Its core focus is retrieving data to build model context and enabling synchronous function calling, giving agents a consistent way to access external systems without bespoke integrations. The agent to agent protocol, or A to A, is an open protocol focused on communication between agents. It enables agents to discover each other's capabilities and request work across different frameworks and vendors. A to A supports asynchronous requests, long running tasks, and coordination across distributed multi agent systems, which are common in enterprise environments. As we'll see, A2A and MCP are complementary, not competing protocols, and both are now Linux Foundation projects, reflecting growing industry alignment around open, vendor neutral standards for agentic systems. So let's talk about MCP in more detail and why it matters for agentic systems at scale. As agents become autonomous, one of the first practical challenges you hit is how they retrieve context and invoke external systems in a consistent way. Model Context Protocol, or MCP, addresses this by defining a standard interface between agents and the data sources and services they depend on. Instead of embedding custom logic for every database, content repository, or API, agents interact through an MCP client, which connects to one or more MCP servers. Those servers expose data and services in a consistent, discoverable way, whether that's raw content, curated data sets, embeddings, or service calls, without requiring bespoke integrations in every agent. A key architectural benefit here is reuse. MCP servers can be shared across agents and applications, reducing duplicated development effort and simplifying operations. When deployed remotely over standard transports like HTTPS, multiple agents and models can safely share the same MCP servers, while governance and access control can remain centralized. The bigger shift is that MCP moves data and service integration from an application specific concern to a platform capability. Agents can focus on reasoning and decision making, while MCP provides a standard scalable way to retrieve context and take action as part of the agent execution loop. Now let's look more closely at A to A and how it enables agents to communicate and collaborate with one another. As agent systems move beyond isolated use cases, agents increasingly need to delegate work, coordinate execution, and collaborate across boundaries. Agent to agent, or A to A, is designed to standardize how that interaction happens, regardless of how agents are implemented or where they run. A to A defines a common protocol for inter-agent communication while allowing agents to discover each other's capabilities and request tasks in a consistent way. Rather than relying on a tightly coupled integrations, agents interact through well-defined interfaces that support structured requests and responses across different frameworks and vendors. A key design goal of ATA is supporting real-world coordination patterns. Many agent workflows involve asynchronous execution, long-running tasks, parallel work, and iterative collaboration. ATA is built to handle those scenarios directly, enabling agents to initiate work, exchange intermediate results, and coordinate outcomes over time. From an operational perspective, A2A incorporates established enterprise standards for authentication, authorization, and telemetry, enabling secure communication and end-to-end visibility into agent interactions. This allows organizations to monitor behavior, diagnose issues, and maintain control as agent ecosystem scale. The result is a protocol that treats collaboration as a first-class capability, enabling distributed agents to work together as part of a coordinated system rather than as isolated components.
Awesome. Hey, John, you just covered this, but we did get a question from the audience. When would you use MCP versus A2A? I think you just covered it, but if you wanted to just say a brief comparison there.
Sure. Yeah. To reiterate, I think what I touched on is, and I know sometimes this is confusing, and this both options are possible. If you're talking about agent to agent communication, you can structure an agent as a tool through an MCP server. However, as I mentioned, a lot of agent to agent interactions require a more complex interchange of messages than what MCP currently supports. So, if it's more of a synchronous function call interaction, MCP certainly can be an option. However, if your use case requires more asynchronous interactions or long running tasks or thing of that nature, then A2A is probably the better protocol to use for agent to agent communication.
Okay, great. Yeah, thank you. There's more questions from the audience, so please send in more questions, please. We will cover, more longer questions at the end. So, but please do send in more questions. Thank you.
Yeah, absolutely. So at this point, we've looked at MCP as a way to standardize how agents access data and services, and A2A is a way to standardize how agents communicate and collaborate. And together, these protocols enable a wide range of multi-agent architectural patterns without tightly coupling components or hard-coding interactions. On the simpler end, you get familiar models like sequential pipelines or an orchestrator pattern where a central agent coordinates work across specialized agents. These are often the easiest starting point for enterprises adopting agentic systems. As systems become more dynamic, you see more advanced patterns like agentic meshes and hierarchical decomposition and iterative collaboration, where agents operate as peers, evaluate each other's outputs, and adapt over time. The key point isn't the individual patterns themselves, it's that these patterns aren't tied to a specific framework or vendor. By standardizing interaction at the protocol level, MCP and A2A let you choose the coordination model that fits the problem and evolve it over time without re-architecting the system. The flexibility flexibility is what allows agentic AI to move beyond isolated use cases and scale into production-ready agent ecosystems. But as we discussed earlier, interoperability at scale involves more than just interaction. So there are projects like the Linux Foundation Agency Initiative that build on the efforts of MCP and A2A to address the broader set of challenges required for enterprise-grade agent ecosystems. That includes agent discovery, identity and trust, and observability across distributed multi-agent systems. The goal is to provide shared foundations that allow agents to find each other, operate safely across organizational boundaries, and be monitored and governed consistently as these systems scale. So with those foundations in place, I'll hand it over to Bindu to talk about what this means for infrastructure and especially storage.
Hey, thank you, John. You guys can hear me?
We can.
Yes, we can. Thank you.
Fantastic. Thank you. Thanks, John. Jumping right into the infrastructure, right? Now that we have covered interoperability and multi-agent systems, let's shift the gears to talk about the infrastructure, especially storage. Agentic AI changes how data flows through an organization. Agents depend on faster retrieval, reasoning loops, and rich context. So storage is no longer a passive, right? It becomes part of the reasoning path itself. So now let's go in. So what we get from the agentic impact to storage, there's two aspects. I mean, it's not the exhaustive list, but that's kind of two buckets we can think of. One is new workloads. With agents, you get new workloads like reasoning models creating unique access patterns for high IOPS key value access and KV cache for offloading to accelerate inferencing. And the second is the context building pipelines, which means agents continuously discovering, retrieving, and enriching data, which drives semantic indexing, embedding, and AI-enriched metadata. What does this all mean? Storage must support both the compute side and the context side of the agentic workflows. Now, let's talk about the aspects of data, right? What customer needs is data readiness for AI. So the other word that industry can refer to is AI ready data, right? It's not just the capacity, but the workflows spans discovering data across, so it's discovering data across silos. Once you discover the data, now you want to make sure you curate the data. You curate both structured and unstructured data. And then you want to make sure you transform the data so that it's available for Gen AI. And when we're talking about available for Gen AI, I'm sure a lot of you have heard chunking, parsing, labeling, and embedding. And you want to make sure you're able to search the data securely by the LLMs. And we also want to make sure we fine-tune the data for fine-tuning and able to create data sets. And we want to make sure we do all of this to make sure that we provide a consistent access control across the different data formats that we have went through. And we want to do it in a way that we are preparing data not just in the cycle, but also making sure the lake itself, data lake itself, is fresh, make sure there is no drift, and make sure there is a cost and capacity monitoring are happening. Now we talk about the data. Now let's go into from the agentic point of view, right? When we're talking about the agentic, as we just talked about, there's one aspect of it, which is the databases, or you can think of the data itself, where a lot of context building is happening, and persistent multiple representations like embeddings, vector indexing, knowledge graphs, and AI enriched metadata. This context layer can add up to 7 to 10 times more storage data than the raw corpus itself, and introduces mixed I/O workloads. No longer a large I/O or small I/O, it's a mixed workloads. So able to support small random lookups to retrieve an agent memory, plus burst large I/O for reindexing, feature extraction, and checkpointing. Let's go a little bit deeper in this context, right? So now, going through the AI preparation phase, step one in AI is really able to create a metadata extraction, right? We have discovered all the data we need, both the structured and unstructured, and we able to ingest and transform. Now the key is to able to identify the data that need, and the main step towards that is really enriching the data, which is metadata enrichment, is one of the industry term used. What it means is we attach semantic labeling, entities, timestamps, relationships, geoattributes, just a few. There is a lot more. Under consistent access control, all of this need to be happen. And the high quality metadata means improves discovery, enables policy engagement, and becomes the substrate for the downstream semantic search and agent planning. Okay, now we talked about making data more smarter, available. Now let's talk about the data becoming more curated. In the curated aspect, we curate the data that's required for a given workload. So you create a curated data set. And what it does is removes any noise, creates a consistent data sets. Now, once you have curated, you want to create a context. And this transforms the general multimodal embeddings, knowledge graphs. So agents retrieve by meaning and reason over relationships. This stage often drives data explosion because embeddings, semantic index, and graph structures are persistent alongside curated data with unified governance. Okay, now we talked about the discovering, making data more smarter, and able to convert the data ready for AI through embedding creations, context. And we want to make sure we make this available. And as John just talked about, we want to make it available through traditional protocols for the agents to make it simple and make sure they are agnostic to the access storage types. So MCP provides a standard access layer by MCP servers that expose consistent endpoints, abstracting source heterogeneity, centralizing governance, and letting agents pull the right layer of context without bespoke connectors. Let's talk about, we talked about the data from the context of data that's get generated. Now, in the context of the inference itself, we have agents likely to use common inference services and reasoning models, as John just talked about, right? And the data explosion as well in this space. Now, one of the examples that we have seen in this is the KV cache. And the KV cache is scaling bottleneck because it consumes expensive GPU and CPU memory. Offloading KV cache to storage enables session scalability and persistence beyond a single node. Distribute access, so multiple GPU servers share the same context. Reduces duplication, enabling load balancing. Also optimize topology, separating prefill and decode without copying cache state. Now, bringing all this together, what does it mean to storage in this agentic world? Storage becomes the semantic backbone for agentic AI. It durably holds raw data, curates data sets, embedding knowledge graphs, KV cache, and other context artifacts. Supporting MCP servers, MCP access, with traditional protocols makes the storage play for AI. At the same time, each agent's private memory embeddings are stored, supported by the storage. The result? Reliable retrieval and consistent use of all representations of data across agents and inference services. In a short, storage is no longer a static play. It becomes intelligent and it needs to support wide variety of workloads along with the data types. With that, I'll give it to John.
Yeah, Fatima, there's a very good question from the audience. Perhaps we could cover that here. So the question is, can you please address in more detail the 7x plus storage requirement you mentioned? Why is that required? With NVMe, that would be rather expensive. So I think the question is asking about storage and what types of media are impacted. Is it the solid state? And I think the part we didn't mention yet is the memory. And so in some ways, it's the impact on holding the context while the process is going. And so I think there's a memory attribute in there as well, if you could address that.
Yeah, so there's two folds to it. I will address the first question, which is why is it 10x or 7x storage? It's in comparison. So you start at raw data, right? You got your documents, let's say PDFs, and you want to feed that to your LLM. And you're not going to just simply search. If you do text search, sure, you can find, but text search doesn't give you the actual meaning of the data that you're looking for that's relevant to the context that a query comes in. So what it ends up to be is you're taking that raw data, you're going to chunk it and create a contextual information out of that data and store it. And this storage usually happens in vector databases, but you're storing both the chunk and the embeddings. And you want to be able to have a faster retrieval, so you have indexing. And there is different indexing mechanisms depending on what resources you have in your system. Say you have GPUs, then you can have an index mechanism that supports GPUs for faster semantic search. But your system doesn't have GPUs, then you can rely on a traditional indexing. Do you have enough in-memory space so you can pull in all the data that you need? If you're not, then there is different indexing mechanism like disk NN versus HNSW, where you can put everything in memory. So depending on the system that you got, you have this one document that's been chunked up. And chunking strategy itself is huge. The chunking it's a strategy of its own. So the semantic meaning of not just a paragraph in your document, but what that paragraph means in the whole document needs to be captured. And that itself increases the number of chunks that you're storing and now changes the embeddings. Depending on the model and the number of dimensions you pick, that increases the storage. Now, you can ask, do I need to store all of this in a NVMe devices, or can I store it in HDDs? Definitely, it depends on what the latency of your application requirements are when you're querying for this data. So there is always a tier aspect associated with. So there is always a newest data or the data that's more important that you can put in your more low latency storage devices, and the data that's kind of you can think of it queried per week or a month and not latency dependency. You can tier it to a lower cost storage. It's all kind of depends on what your workload looks like and what's your application performance and latency looks like. Hope that answers your question. And then we're talking about the KV cache, right? The memory requirements and the GPU resource. You don't have all the memory to store all the tokens and the context that you're generating. And you're tiering it to multi-layers. So you can move it from GPU memory to the CPU memory, to the local drives, and then to the network storage. And you can do it in a way either depending on your access pattern or depending on your latency. And that's another use of the storage, why it increases. And depending on your workload, if you're doing LLM and if you're doing reasoning models that generate more tokens, now you need more storage and you want to reuse those tokens because generating them, you need more GPU and more power versus reusing them. Hope that answers the question.
Great, thank you.
So yeah, no, great questions. If you have many, we can go over after. So with that, I hand it over to John to bring it home with the summary.
Great, thank you, Bindu. So as we've discussed, Agentic AI is a rapidly advancing technology that stands to impact enterprise storage across multiple dimensions. So as Fatima described, Agentic AI is the next wave of AI technology evolution. The agent's ability to autonomously reason and act enable them to automate, an ever-expanding range of complex tasks. We learned that solving enterprise problems is going to require diverse and distributed multi-agent systems, and protocols like MCP and A2A help enable that. And finally, giving agents the ability to discover, process, or retrieve data from storage in real time based on task-specific needs will require semantic data awareness, new interfaces, and new capabilities. So we think storage will play a key role as agentic AI continues to evolve. And of course, all of this is advancing at such a rapid pace. It's sometimes difficult to know how exactly this will play out, but we're all very excited and working hard and exploring the possibilities. And so with that, I think we can transition to questions, Michael.
Great. Well, thank you so much for this great information. And let's move on to the Q&A session where we welcome more questions from the audience. And please let us know where we can add additional focus. So we did, let's go into some of the questions that are, John, I think you answered some of the questions through chat, but let's maybe bring that to the full call here. What does the mixture of experts, MOE, does that require or need A2A versus MCP or both still needed?
Apologies, my network connection dropped briefly. Did you want me to restate some of the questions, the answers I put in the chat?
Okay, yeah. So on the question you answered in chat, but it's the MOE, does that require A2A versus MCP or both?
Yeah, so that was a great question. I'll briefly summarize the response that I gave. So mixture of experts is a technique that basically reduces the amount of computation that has to happen when during inference time. And so it's something called sparse activation. The way to think about it is that the model is structured in a way where you'll have, let's say, like a billion parameters, and those parameters are encoding whatever information was a part of the training set that was used to train the model. But at inference times, some of the tokens are routed to only some of the parameters. So let's say instead of all billion parameters being computed at inference time, only half of them are. And so it lets the model represent more information without processing all of it for every token generation, and that's a much more efficient inferencing workload. Now, in regards to MCP and A2A, both protocols could be used to interact with an agent that's using an MOE model. They're somewhat orthogonal activities. One is how MCP and A2A are about how agent is asked to do something, and then the MOE model is basically how the agent actually goes about reasoning and generating all the tokens it needs to come up with a plan and figure out what it has to do. So I hope that answered the question. And if not, reach to me offline, and I'm happy to try to go into a more complete answer.
Awesome. Yeah, thank you. And so we have another question. John answered it through chat, but let's maybe review it here. Do reasoning models follow the complete observe, reason, act loop for each and every iteration of the auto-regressive loop? If not, how is the number of iterations decided? How is the choice of reasoning step made in the MOE models?
Yeah, it's an excellent question, and I'm realizing I didn't actually answer the second part, so I'll do that now. Um, so the way all these models work, they're called autoregressive because they look at their past output to generate their next output. As some of you may be aware, that's done on a token by token basis, where a token, think of it as a word. It actually can be smaller than a word, but it's just easier to think about these words. So um, you can think about the sentence of why did the chicken, entering it into an LLM model, it might predict that the next word is cross, right? Because it's seen the joke, why did the chicken cross the road, probably a million times in its training data set. Okay, so that's called an regressive inference because it looked at the prior input and then it predicted the next output. That's the way to think about this in terms of the agentic loop is once the context is built, either from the user's original prompt or as a prior iteration of the agentic loop where some context has been retrieved with the tool, all of that's kind of put together, fed into the model, and the model sort of chews on that. It keeps generating tokens until these models are trained and built in a way where they usually emit some kind of token that says I'm done. It's like a stop token. Or they reach the limit of number of tokens that they can generate because all these models have a limited context window length. And so usually it's the stop token. And that stop token will then sort of say like, well, what does the agent want to do? Does it want to do a tool call? And that's usually structured as some kind of like, you know, uh, JSON text in the model's output, and the inference server knows how to interpret that and say, oh, okay, that's a tool call. Let's do that. Or it's the actual final response, in which case, that response is just sent back to the user. So the auto-regressive part is really happening in that reasoning stage. And, it's the models themselves that say when they're done, unless you have some other limit that you've put into place, like the number of the context length or something else. So hopefully that answers the question. And if not, like I said, happy to add more detail offline.
Awesome. Yeah, thank you, John. And then going back to another one you answered in chat, which type of storage is needed for raw KV data or context data? Is it SSDs or hard drives? as a storage vendor, what types of workload should we be validating? I probably mispronounced part of that question, but go ahead.
I think I kind of sorry, go ahead, John.
No, go ahead, please. I was going to say you can take it.
Okay, yeah, I think I kind of covered it. I kind of responded, but I'll call out here. Workloads perspective, you got vector databases in terms of the some of the workloads, knowledge graph, as well as the inferencing and agentic, right? And in terms of the storage type, what we're talking about is, in this case, storage is not why it's required. Storage is not a requirement, it's a necessity. These applications are generating so much of these workloads, generating so much of data, they need to persist it for the reuse and for the efficient performance of the LLMs and other services. And at the same time, not all data is equal. Depending on your application, a lot of these workloads are actually implementing tiered model, where you define the data and it's QoS or it's gold, bronze, goes back to medallion, and you can tier the data to low cost. But you do need, depending on your workload, but a lot of the real-time workloads do need performance storage.
Okay, thank you. Okay, so let's see. Let's go back to. So these were not answered in the chat. Is there an I/O tool which SSD storage vendors should be using or validating? And then more random random read or write or both. What is the percentage of read and write?
So talking about the tools for storage performance, there are, machine MLPerf is one of the leading in those benchmarks. It has support both the storage and also inferencing, but it also coming up with the vector performance tool as well. Vector DB Bench is one of the ones you can use. MLPerf is one of the ones that you can use, to name a few. I think the other question, the other part of the question I'm trying to remember, what was the other part of the question?
They're asking for the percentage of read and write, and is this more random reads and random write, or which kind of profile for I/O?
Depends. I know that's not the answer you're looking for.
Yeah.
But because it depends on the workload, right? And if you're looking at vector databases, the modern workloads kind of comes with the small I/O random, and some of the training workloads it supports large I/Os. So that's what I kind of said in the slides. As a storage system, you kind of need to support all the type of workloads. It's no longer I'm a sequential, I'm only supporting mixed, and 80% read write. You can think of 50% read write possibilities there, depending on your workloads. But it's the spectrum is larger than what it used to be. John, anything you want to add there?
Yeah, it is a challenging question to answer, and myself and some other colleagues from Dell have done prior SNIA presentations on the details of some of those workloads. And it really does depend. If you're doing training, you tend to see very large sequential workloads that are almost 100% read or 100% write. Those training jobs are designed to avoid random IOs and multiple writers to single files, because those are traditionally hard to get high performance out of. But then when you get to inference and you start talking about things like vector databases, as Bindu mentioned, that those do tend to look like more traditional enterprise workloads. Obviously mostly read if your vector database is somewhat stable and is only updated every once in a while. And even there, it gets hard, because if you're using a vector database that comes from a traditional, relational database heritage, then you're going to see some very, familiar database like workload patterns. But if you're using a vector database that comes from a more cloud-hosted origin that's using object storage, it could have a very different workload pattern. So, that's one of the challenges of this space, is that, each each sort of operation that you might do might have a very different workload profile and requirements from a storage perspective. But that's what, at least our team is spending a lot of time trying to understand. And so, the good news is that, solutions exist, and folks are building very capable systems.
Okay, awesome. We have a follow-up question. How is the KV cache stored, as blocks or objects or files? And why is this? And which data structure is used to store on disk, like radix trees, B plus trees, hash tables?
I mean, yeah, go ahead.
No, go ahead. You might have a.
I don't have a very clear answer either for how it's stored. It depends on the storage implementation at the end of the day, right?
Yeah,
that's what I was going to answer.
Yeah, unfortunately, I think the colleague that would know how to answer that question isn't here on the call.
Yeah, let's do it on the Q&A blog. That's a good solution there. But thank you for the excellent question, and please send in more, because that's, we're just delighted to get these questions. That's great. Okay, we're really getting into the store. So here we go. Since we're all storage nerds, how do these workflows interact with various storage protocols like NVMe, TCP, NFS, version 4.2, S3, etc.?
I mean, I'll start going, and John, jump in at any time you see needed. In terms of the protocols, all are valid, but depends on some of their workloads. A lot of the cloud native workloads, they're coming from cloud. They heavily use S3 for its simplicity. That's one of the observations we have seen. And at the same time, there is a performance aspect, and I know SNIA has a tweak going on, which is also looking at S3 RDMA and some of those enhancements as well. But a lot more traditional protocols are supported. But if you want a lot more richer feature functionalities, that's more seems to be driven towards S3.
Okay. Well, thank you. Yeah. And then go ahead, John. Did you want to add?
I was going to just try to briefly add that, it's essentially, in my opinion, a mixture of scale out file and object, parallel file systems, and traditional, NAS or block systems, right? Depending on which part of the problem you're talking about. So as Bindu mentioned, there's a lot of interest in using S3 as a protocol as a data scientist, because I can say, like, it's super easy for me to access data, right? I don't have to worry about mounting a file system. I can just, all I need is a URL and some credentials, and I instantly get access to data. So from a operational perspective, it's super easy. However, what we find is when performance becomes a key factor, there's still a tendency to fall back to NFS, because then you can get things like RDMA. And so you can get more performant access to data for either feeding the GPUs during training or syncing checkpoints or things like that. It's interesting now that S3 is adding RDMA capabilities that maybe we'll see a shift in behavior there. When you get to things like KV cache, where you might be talking about a lot of data that you might be syncing or reading as inference workloads might be moving across GPU servers, then you're going to start seeing like really high performance storage like requirements. And so that's where that comes into play. And then, as we talked about with vector databases, a traditional transactional file system like NFS server, or even a block server, if the database is going directly to block, like, might come into play. So it's really like, it's like the whole zoo, like all of the storage stuff comes into place somewhere. And I think anybody that's been in this industry for a while understands and appreciates that you can't build one storage platform to do it all. So you really are talking about an ecosystem of platforms that together form the infrastructure needed to host such a diversity of workloads.
Okay, awesome. Okay, so we're running at towards the end of the talk right now. So one last question. Is there a MCP-based API that represents agent interaction for read-write data? For example, put, get, POSIX, like, if we could just maybe 2 minutes on that, please.
Yeah, so I guess the way I'll answer that question is that with the popularity of MCP, you're seeing a whole bunch of MCP servers being created around access to data. So, for example, there are certainly MCP servers that you can download, install on your local system that will give your, agentic coding assistant access to your local file system, and it can do everything you said. It can, list files, read, write them, and things like that. Um, in terms of accessing like common databases and stuff, there are MCP servers out there that are starting to emerge that front end some of those enterprise data systems with primitives like either reading files or writing files, or if it's a database, doing a query, submitting a SQL query. So there's a lot of diversity out there. I think honestly we're still trying to navigate this. Security is like the biggest thing right now. If you think about it, we've had like mature protocols for accessing databases for decades now that again like know how to do like role-based authentication or things like that. MCP is sort of emerging and disrupting some of that. And so, putting an MCP server in front of your like production or enterprise data, it may be stored in an enterprise database without having such rich security controls is sort of something we're still navigating and solving. So I guess what I'm saying is there's tons of options out there. Designing these systems really does come down to what are the primitives this agent needs to get the information that's required for it to do the task that we're asking it to do, and then you can search for whether or not an existing MCP server exists that gives you those primitives, but also supports the security that you need. So it's I don't know if that quite answered the question, but it's such a dynamic and evolving space that honestly, whatever answer I gave you today would probably be wrong tomorrow.
Yeah, and we can add more flavor on the
Sure.
Q&A blog. Thank you. Well, thank you very much to our experts today, and this has been fantastic discussion with just excellent data. And I really appreciate your time and effort to do this. And thank you to our audience. Thanks for joining us. Please remember to rate this webinar as this is very important to get your feedback. This helps us to get better content over time. So please remember, you can always download this presentation and many other items at our educational library, as well as follow us on X. And thank you again to all one more time, and have a great day. Thanks again. Bye-bye.
Thank you all. Bye.
Thank you.